Okay, so hello everyone. I'm Ben Chen, a final year PhD student from Nanyang Technological University, Singapore. Before I start my presentation, I want to like my great partner Rui to introduce himself. Rui, would you like to say hi?
Sure. Hello, everyone. I'm Rui, a PhD student at University of Texas at Austin.
Okay, thank you, Rui. Actually, our work is a highly interdisciplinary topic about the optical imaging and the microscopy. I think a lot of audience here are not familiar with our research area. So in the following talk, I will try to use the simplest word to introduce the background and the essential information from a physics perspective, which I think it could be helpful or at least interesting for you. And then I will hand it over to Rui to discuss how to use our dataset and the results from the AI aspect. So let's explore the tiny world. Just for now, with our naked eyes, I think the smallest thing you can observe maybe is your hair, which is around hundreds of micrometers. Smaller than that, you have to rely on some tools, for example, the optical microscope, which is quite often in the majority of the research lab, hospital, and the industrial. However, light has the limitation. In simple words, the object smaller than half of the wavelength of the light cannot be resolved with an optical minor, which is known as the optical diffraction limit. So considering that if you are using a visible light, the smallest thing in such a case you could say is just around 200 nanometer. Actually, beyond that, you can use the electron microscope, which can easily offer you the resolution of several nanometer or even in a picometer scale. So people may ask, why are you still interested in pushing the boundary of light? Because you have the solution of the electron microscope. The answer is there is a fundamental trade-off between these two techniques. So let's have a specific example. Considering that you want to characterize a biology sample, let's say a virus, and this is an image of the COVID-19 virus under the electron microscope. It is a high-resolution image, but unfortunately, the moment you saw this image, this virus has been killed due to the high-power electron beam. So in contrast, the optical microscope is the non-invasive technique, and it is user-friendly. Even a schoolboy can play with that, and it is low cost, but with the limited resolution. So the motivation in our research field is quite straightforward, which is when you decrease the sample size, in other words, you want to see things smaller and smaller, can you keep the non-invasive and the high resolution at the same time? Actually, there has been several fantastic techniques towards this goal. For example, the near-field scanning microscope and the fluorescent-based super resolution microscope, the Storm and the Stab, which win the Nobel Prize in chemistry in 2014. However, a similar challenge shared by them is they are still highly risk to influence your sample or even destroying your sample due to the near-field probe or the fluorescent labeling. So here, what we want to deliver is a fully new, label-free, non-invasive, far-field optical imaging technique for the scientific community. And for the CV community, this is the first general public optical imaging dataset and AI benchmark beyond the diffraction limit. And we really love one of the audience in this year of the CVPR conference. We have a big talk, and he finally comments this work by saying, it is the eyes for AI to see the nano world now. So let's go to the detail about this work. Here I have a very concise traditional optical microscope. I'm trying to use the simplest word to describe it. So just consider you have your light source to illuminate your sample, and followed by a common imaging system, you can collect the corresponding optical images with your camera. Normally, most of the people will try to get the best forecast images. But what we are using here is the defocused scattering pattern at the far field. So why we want to use the scattering pattern? This is a very interesting project. I'm not sure if you can see the video now. Yeah, let me play that. There is some technical issue. Okay, can you see now?
Yeah,
Yeah.
I don't think
Okay, you
yeah.
can see the video now. So actually 4 years before, when we were using the AI in the semiconductor industry application, our group did a very interesting project by fabricate such a lot of single nano slit with which the width of the slit is just several nanometer. And we want to characterize it because we want to see if there are any defects or the mistake during your manufacturing. Normally, the industry will mostly rely on the electron microscope. So in such a way that you have to operate in the vacuum system and you have to use a very expensive setup to have such a clear image. And in comparison, this is what you can see in this video using an optical microscope, but collect the image at the different heights, from the unfocused 0 lambda to the far field of the 10 lambda away from the sample surface. And our project is to using AI to analyze this data. It was a really, sorry, it was a really big surprise that we found the accuracy using the AI and the scattering pattern can even beyond the electron microscope. So followed by a lot of findings and the experience like this in the optical domain, just in the last year, we achieved the first universal imaging technique, which we named the OpticalNet. So in this project, we designed such a fundamental building block, an array of the square, which the size of this single about this single square is sub-wavelength is just 180 nanometer. The light we use for this project is 640 nanometers. So the size about this square is sub-wavelength scale. So you use your light to transmit this binary object and get your optical far-field diffraction pattern. The target of the AI here is to retrieve the central area which we are interested from such a blur, even an abstract pattern. So next question is how we're going to use that. After you AI model learn the dataset of this very simple basic building block, and during the training process, trying to link the interrelationship between this optical diffraction pattern and the building block image, now you can offer a practical arbitrary shape object, but with the sub-wavelength scale for the testing. So how to do so? You use the same light condition to do the scanning about your sample, and each sub area about this sample will result in the corresponding diffraction images. And you send these test diffraction images into your trained AI model, and it can offer you the prediction one by one. And finally, you can stitch these predictions with the same spatial coordinates and get the whole pixelated sub-wavelength imaging. Just like a schoolboy play with a Lego, the fundamental building block can construct a very complex object, and we just adopt actually a very similar idea, but in the imaging domain. So I think this is all the information and the background, and also the initialized idea about this paper. So next, I will hand it over to my partner Rui to discuss how we're going to use this dataset and the results from the AI perspective.
All right, thank you very much, Ben-Chan. After understanding all the overall idea that we aim to image arbitrary shape beyond diffraction limits, let me now walk you through the composition and the utilization of our datasets. Our OpticalNet datasets includes both simulated and real experimental data. We divide them into three categories: the block, the light, and the SimStar, which is the SS. Among this, only the block dataset is used for training. It consists of like the randomized square patterns that are the fundamental building blocks of how the AI learns. So the format is pixelated, and you can think of them like the Lego pieces that teaches the model about the basic sub-wavelength diffraction pattern in a window way. So that is both modular and interpretable. And to evaluate whether the model can generalize from these building blocks to unseen complex shapes, so we designed two special test examples. The first is light and artistic calligraphy patterns that aims to test the model's ability on intricate curves and geometries. And the second one is SimStar, a standard optical resolution benchmark where the lines get closer as they approach to the center, which means we require higher resolutions to distinguish them. So both patterns are fabricated or simulated to be fabricated to mimic the real examples. And we provide 66 by 66 scans, which is composing of 4,300 in total scan example for each. So together with the public simulation frameworks that allows you to create your own customized patterns, these three data sets together forms the foundation of our optical net. Now, let's take a look at our ground truth labels or the object image. And why do we offer them in different sizes? So in the center of the figure, we can see that a diffraction image is formed where the incident light intensity is the highest in the middle, roughly in the 3 by 3 area. However, the diffraction pattern we observe isn't just determined by the central region itself, but rather it is a result of complex interference, including the contributions from the surrounding pixels. So we provide three types of the ground truth windows. Each of them represent the trade-off between the focus of the beam as well as the surrounding context, where the 3 by 3 settings requires the models to focus on the light center, but exclude some of the neighbor informations. And in the 7 by 7, we have this wider fields but it also receive like weaker and more diluted signals about the centers and the edges, which the model may find it useful, but they have to ignore the noises. And the 5 by 5 is more like a in between of the surroundings and the focus. And at the right, we have the distribution of the samples in the count of white blocks in the composite data sets. Since the fabrication is at the random pixelating pattern, it is therefore a binomial distribution with a probability of half. Hence, it forms kind of like a Gaussian shape with the histogram. Note that we intentionally include more full black samples, which is highlighted in red. These are some of the scanning that's from the unpatterned regions to serve as the useful backgrounds of the negative signals to help the models to distinguish the noise from the real pattern. And let us talk about the training. The slides now illustrates that the end-to-end pipeline of the optical nets, from training of the optical building blocks to interferancing the reconstructions. So we begin the training with the diffraction inputs consisting of all the small squares and their corresponding object images. And together, these pairs are used to train a neural network in an image-to-image translation task to complete. And we have this diffraction pattern from the diffraction pattern domains to the object domains. And since the ground truths are in binary, we use pixel-level BCE laws for the training. And once the model is trained on these simple square patterns, we use them to perform inference on the diffraction images we collected from the arbitrary shapes. For example, the light patterns we have seen here. To do this, we scan the complex shape regions and continuously and producing the diffraction images for many small overlapping patches. And each of the patch is passed through the model to generate local predictions. And these predictions are stitched together to reconstruct the full object image on the right. To reconstruct a complete high-resolution, high object image, we need to stitch them together. And how do we do that? So let us focus on the red square over here, which represents the pixels that we wish to see. That single location isn't predicted from just one input, but multiple overlapping blocks shown in the yellow boxes, which we call as the neighborhood of the red square. And each of the scan of the blocks produces its own diffraction pattern, which is then fed into the train model. The model outputs a prediction image, and from each of these, we extract the predicted value at the relevant locations, and we take the expectations of the red squares out of all the relevant predictions in the neighborhoods and effectively combining the guidance from the multiple perspectives. So you may think of this reconstruction process as kind of like the mixtures of experts, where each scan offers kind of like a slightly different view of the target pixels, and their collective votes leads to more stable and accurate results. And as our result of stitching and reconstructions, we obtain this in the pixelated grayscale images. And because of this pixelating method we use, the output is not only continuous and are having this mosaic patterns. Nevertheless, I believe you can see that it still captures the essential structures of the objects at the 66 by 66 resolution, which we can see that it is already quite clear and representative of the sample. And as you might have noticed that we repeatedly use this ring-shaped pattern that is called a Siemens star through our evaluation. And why is that? So the Siemens star is a well-established resolution test pattern in optics. It contains many of the radically arranged spokes that get progressively closer as we approach the center of the circle. And as you move inwards, the spatial frequency increases, which requires higher resolutions to see them very clearly. And as the scanning process on the left, we raster scan the Siemens stars with a sub-wavelength beam and with a step size equals to 1 wavelength, generates a diffraction pattern, and which the model gives the local predictions, and combining them, we got the final image on the right. And we can now quantify this resolution computationally. So if the model can still distinguish the epoch as they converge towards the center, they have like succeeded in resolving features smaller than the diffraction limited, which we can find by some techniques on the rings. So this makes them not only intuitive patterns for visual inspections, but also a quantitative benchmark for sub-wavelength images. And let us take a look at the experimental results. We will start with the simulation results first. And here we evaluate 5 different models on the block, light, Siemens star test sets. So the first 2 are the UNet-based models that is a very conventional way for the image translation task, which is rest UNet and attention UNet. And this model takes the diffraction image as the inputs, and through the unit shape of encoding and decoding, they predict the corresponding object image with the pixel-wise outputs. And we have this ResNets 18 and 34, which also adopts encoder and decoder styles ResNets with skip connections, and but it is like a more traditional way, but effective backbones. And finally, we have our own design latent space transformer, which models the long-range dependency across the spatial grid. So potentially more aligned with the global interference nature of our reconstruction and stitching. So we measure the performance using 3 traditional fixed ground truth image-to-image translation matrix, that is accuracy, macro F1 score, and the Jacquard index. Among the models, the transformer performs the best across all the matrices, which are more sensitive to the pixel level structures than the accuracy. And at the bottom, we can see that the visualization predicted by the transformers. So we can see that like in the light examples that it recovers the curve, and in the SS samples, it has the radical structures, and as we near to the center, the resolution demands is the highest, and we can still see some of them very clearly. And let us move on to the experimental results, where the things get more challenging due to physical noise and fabrication imperfections, and maybe because of the system level distortions. So each of the roadblocks here correspond to a different ground truth window size, 3x3, 5x5, and 7x7. So we can see that how the context size affects the model ability to recover the fine details from those images. And across the board, transformer consistently achieve the best performance. And this confirms its ability to model the long-range diffraction dependencies, even when the signals are subtle and corrupted by noise. And we also have some of the qualitative comparisons of the reconstructions done by the top 2 performing model, ResNet 34 and the latent transformers on our experimental scans. You can see that the transformer reconstruct a sharper edge and clearer features, especially in the Siemens stars, where it resolves further inwards to center, which demands finer resolution. And the light pattern is also more preserved, where we can see like the lighter strokes and higher constructs. And in the meantime, there are like less background noise in the output that is produced by the latent transformers. And that's wrap up my part of my presentation. And thank you very much for following along. I will hand back to Ben-Chan again, who will recap and summarize on the key takeaway of our work.
Well, many thanks, Rui. So I will do a final summary. So actually, we are doing the AI for science, so they require a lot of domain knowledge. I'm not sure if you catch the basic idea about this paper. So the first key point I think is for some audience who have the background of about the optical imaging or who have tried the microscope by themselves. So this is a new non-invasive, label-free, and far-field optical imaging technique, in contrast with the existing optical resolution method. And for the second one, I think would be benefit for the general AI community is considering that you just have limited data, but you want to have a more and more generalized or even a universal imaging technique. So how you design your training library, what kind of the such prior information that you want the AI to obtain. So in our simple project that we experiment to demonstrate, you may don't need to have more and more data and just considering to have some basic building block and construct based on it to the arbitrary shape object. And the third one is we really want to introduce our topic into and attract the attention from the computer vision community because we all deal with the image, but just people from the CV mostly play with the computer generated image, but we are working on a more specific area. We are deal with a size in a very tiny scale. So this is the general and the public optical imaging dataset and the AI benchmark. We are not targeting on the specific research area, and this microscope system is quite often in the majority of the research lab. So once this AI model established that you can easily integrate with your existing microscope in a lot of hospital on the industry. So we really wish the future collaborator or people who are interested in this topic working on this and develop a better AI model. And I think there will be a great potential commercial applications on this topic. And I think that's all about our talk. Thanks for your attention. Thank you.